Hello class, welcome back to Introduction to Material Science Engineering. Today we will be talking about the use of phase diagrams. Phase diagrams are exclusively the province of thermodynamics, which means that everything that they predict for you only happens when your system is at equilibrium. This becomes important when we talk about processing and heat treatment because quite often we will deliberately deviate from equilibrium in order to prevent equilibrium structures from forming. But when you look at a phase diagram, whatever the type, you have to remember that what that diagram predicts will only come about if all of the processing changes, such as changes in temperature, changes in pressure, changes in composition, are done very, very slowly, such that all of the material processes that keep composition uniform can keep up. And in many cases that can be achieved by very slow cooling in a furnace, slow pressure changes, mixing components very slowly so that heat can escape, etc. So for our purposes, for heat treatment in metals, that will usually be accomplished simply by cooling slowly. But as we get into Chapter 11 and we start talking about non-equilibrium phase transformations, especially in steelmaking for hardening and the Martensitic transformation, we'll be sure to point out what happens when you cool quickly or slowly. But today's discussion, slow cooling, all equilibrium. Okay, we have a passel of new terms to define here, all that concern themselves with what we call phase equilibria. Some of these you may have touched on in your chemistry classes, but we're going to go over them just to make sure. Phase equilibria will effectively be concerned with what we call solubility limits. And you saw a little bit of this in our discussion of solid solution alloys, both back in our chapter on crystalline defects, and also with respect to solid solution strengthening in our chapter on strengthening mechanisms for metals. So just to drop back a little bit, we're going to define a solution as a solid, liquid, or gas which has only one phase, not a mixture which can have more than one phase. So basically it's a bit recursive. So a solution will typically be clear, it will be one component dissolved in the other. So we'll start out with a little example that everyone's probably familiar with, sugar and water. Everyone knows that sugar will form a solution in water, a syrup. So it's not cloudy, but that you can reach a solubility limit by either dumping too much sugar in or by cooling it down if you've already dumped a lot in and maybe at high temperature. So we'll define the solubility limit in this sugar-water case as the maximum concentration of sugar for which you don't have any sugar precipitating. And this can be generalized to be defined as the maximum concentration for which only a single phase exists, no matter how many things you have dissolved. You could have one or two things dissolved in another. So you could have multiple solutes in a given solvent. And the solvent in this case is usually defined as simply the majority phase. And again, you may recall having heard that from our Hume-Rothery solid solution rules back in solid solution defects and alloys earlier in the course. So looking back at our sugar-water phase diagram, we have composition on the x-axis, and this is weight % of sugar. So over at the origin, where it says water 0, that's 100% water, all sugar-free. And then completely over on the right, you have 100, where it's all sugar, so it would all be a solid crystal of sugar. And then varying proportions of those two as you go across. And then temperature in degrees C on the y-axis with 100 degrees C up at the top, so that's a boiling point of water if nothing's dissolved in it. So if we go from left to right, we're increasing the amount of sugar, and if we go from bottom to top, we're increasing the temperature for a given ratio of sugar to water. And you can see there's a dividing line there in the light blue, the solubility limit. So everything that is sort of above and to the left of that would be a liquid solution with two components, water and sugar, water probably being the solvent and sugar probably being the solute. And then over on the right-hand side and a bit downward, you have two phases. You have a liquid, which will have both water and sugar, and then a solid, which in this case is going to be pure sugar, but in other cases isn't necessarily going to be a pure compound. So we could ask ourselves a question: what is the solubility limit for sugar in water at 20 degrees C? Well, to find that out, we could use this diagram by simply drawing a horizontal line, which we just did in the animation there, at 20 degrees C, and seeing for what composition on the x-axis it intersects the solubility line. And we look down, you can see the vertical line that was just drawn, it's 65%. So you can dissolve up to 65 weight percent of sugar in water at 20 degrees C. If you go more, you're going to end up with two phases, a sugar-water liquid, and then an all-sugar solid in equilibrium with one another, dynamic equilibrium. So, and there's the answer in written words. So we can put forward a couple more definitions here, define a couple more terms: components and phases. So you saw from our sugar-water diagram, we were looking at water and sugar as being two components of the composition of the overall mixture, which could then be a solution, or it could be a mixture of multi-phase solutions. So we define components as the elements or compounds which are present in an alloy or any kind of combination of solutions and phases. So in the case of sugar and water, water was one component, sugar was another component. If we have, say, a binary alloy, an aluminum-copper alloy, aluminum would be one component and copper would be another component. Now, when we mix these components together, sometimes they'll form a solid solution or a liquid solution, and sometimes they'll form multiple phases, each of which will be a solution with a different composition. We define a phase as a physically and chemically distinct material region. And I'll add, these have a boundary. In a precipitate, for instance, in our sugar, the boundary was the boundary between the solid sugar and the liquid syrup mixture. In the case of this copper-aluminum microstructure that you can see here, which is probably at fairly high magnification, at least 1000x, you can see that the optically distinct regions are multiple phases in the microstructure that have different compositions. The alpha phase is very likely to be an aluminum-rich phase, and the beta phase is probably an ordered intermetallic of aluminum and copper that'll function a bit like a ceramic. So they have distinctly different compositions, and they definitely have a boundary around them. Okay. Going back to our sugar-water solution, we're going to start looking at the effect of changing what we call state variables. If you've taken some mechanical engineering classes, you might be used to hearing about state variables in terms of enthalpy and entropy. From your physical chemistry courses, you're probably used to hearing about state variables, again, in terms of enthalpy and entropy, but maybe also Gibbs free energy. Ones that are more common are temperature and pressure, and in this case, composition. If you're a chemist, you're probably used to hearing about the more general state variable for composition as chemical potential, or the change in Gibbs free energy with number of moles. Phase diagrams concern themselves with which phases are stable for a given set of state variables. So typically you'll see phase diagrams that describe which phases are present over a range of concentrations as a function of temperature or pressure. In most material science processes, pressure is equal to 1 atmosphere. Most of your factories run at 1 atmosphere here on the surface of the Earth, although of course if you're using a hydroclave or an autoclave, say to do a cure on a composite, you might well run into much higher pressures. A geologist will definitely end up looking at very high pressures for the phase stability of their minerals and rocks, especially down in the mantle. But for the purpose of this course, we will be assuming 1 atmosphere of pressure and then only looking at the effect of 2 state variables, temperature and composition. We won't even get into chemical potential, which is a little bit more complex than composition. So 2 state variables only, temperature and composition. If there's an exception to that, we'll point it out and then point out how analogous it is to temperature and composition. Okay, getting back to our sugar-water phase diagram, we can look at how altering the temperature can change number of phases as well as what is stable. So we're going to do a little animation here. So we're going to look at the effect of heating up about an 80 degree C temperature increase, starting at 20 degrees C with a 70% sugar in water mixture, which at 20 degrees C was a 2-phase mixture. As we increase the temperature somewhere around 60-65 degrees C, eyeballing it, we cross the boundary into a region of the phase diagram which told us that only 1 phase was stable. And certainly that was true up around 100 degrees C. So what happened? We changed from a 2-phase stable solution to a 1-phase stable solution. And on a microscopic level, what that meant was all of the sugar precipitates, the single-phase sugar particles that were probably about 100% sugar, maybe had a tiny bit of water in that solid, dissolved. And now we had a liquid that was water and sugar that had a higher concentration of sugar than the liquid which had been in equilibrium with the solid sugar down at 20 degrees C. We can do the same thing by changing composition. So we're looking at another animation here. If we have a path from B to D, so B was our orange circle at 70% sugar and 100 degrees C. If we were to add some sugar, so we went from 70% sugar to 90% sugar, but we kept the temperature the same. So we only changed 1 state variable at a time. We would go back into our 2-phase region, because somewhere around 80% sugar at 100 degrees C, we would exceed our solubility again. And now we'd be back into a 2-phase region, which had, if we look at the purple dot, by adding sugar up to where our average composition of the whole mixture is 90% sugar, we'd now be split between a bunch of pure sugar precipitates and some syrup liquid that had somewhere less than 80%. But the total of those, based on the ratios, would add up to 90% for the overall mixture. So we can go from single-phase regions to 2-phase regions and back by changing either of the state variables prescribed on the phase diagram. If we changed another state variable, say we put this solution into a pressure cooker and we changed the changed the pressure, this entire phase diagram would then not apply. We would have to be looking at a phase diagram that represented the pressure that was being given to us by our pressure cooker. So when you look at the state variables that are shown on a phase diagram, there will usually be a note, if you're looking at one generated from someone else's data, which other state variables are assumed and their values. So like I said, not knowing anything else, you can assume that anything in this class is going to be at 1 atmosphere of pressure. But if that ceases to be the case for whatever reason, you can no longer use the values coming from your phase diagram. A word of warning. Okay, so stepping back and looking at a very classic system in metallurgy. This is the copper-nickel binary phase diagram. This is, if you remember from our discussions of solid solutions in defects and solid solution strengthening, this is a noteworthy system in that these two metals are completely soluble in one another in the solid state. So they don't ever form 2-phase solution. They stay single phase all the way across the phase diagram. And now we can actually see this. So we have weight percent nickel on the x-axis in this diagram. If we're over to the left where it's 0, that's 0 weight percent nickel, which means 100 weight percent copper in this case. And then over to the right, no copper, 100% nickel. And you can see there are no phase boundaries until you get to 1100 degrees C, and then all you have is the liquid solid from melting whatever composition we have. So in the solid state, we don't form any different phases. It's all the alpha face-centered cubic solid solution. Now we can get a liquid phase if we raise the temperature. If we have pure copper, we're going to get a liquid starting at probably right around 1100 C based on what I'm seeing on the diagram, and at about somewhere between 1400 and 1450 degrees C if we have pure nickel. Now in between that, the onset and completion of melting or solidification changes depending on our composition. So we will have a two-phase region, liquid plus our alpha solid solution, depending on our temperature and our composition within that region. So we'll do some examples with the animations on this diagram to take a look at how that works. And just a couple more words from the slides here. As I mentioned, this is called a binary system, and that means we have two components, in this case copper and nickel. Our sugar water system was also a binary system because it had only two components, sugar and water. If this were, say, a three-way alloy, say we had copper, nickel, and aluminum, that would be called a ternary system, and 4 would be a quaternary. Those are much more complicated diagrams that slice usually at single temperatures and use a triangle or more complex arrangement to show phases. We will only be working with binary systems in this case. And as we mentioned before, we have two independent variables, temperature and composition. We're assuming pressure is 1 atmosphere. Okay, so focusing on it on a clean slide here. So binary, two components. Because we don't have multiple phases in the solid state, we only have liquid and then a single solid phase. This kind of phase relationship or phase diagram has a special name. It's called isomorphous, which literally means the same form. So it's another way of saying it's single phase across all compositions. Okay. So now we're going to look at what happens in that two-phase region that has liquid plus our alpha face-centered cubic solid solution, because that is a two-phase region, and we have to know how to walk our way around two-phase regions in terms of how much of each phase is present, and then what's the actual composition of each of the two phases that are present. So we're going to again have some animation. We're going to look at 1100 C, and we're going to look at a 60 weight percent nickel overall composition. So that would be shown by a single point on the phase diagram, the sort of pink point that you can see there, point A. So at that temperature and composition, we have one phase. It's a face-centered cubic solid solution. We'll call it alpha. Typically Greek letters are used to indicate phases, by the way. So you'll see liquid for liquid, and then alpha, beta, gamma, delta is the typical sequence to name your multiple phases. Okay, and we'll look at another scenario where we have 30 weight percent nickel and a little hotter, up at 1200 degrees C. And you can see, unlike A, composition and temperature combination B is in that two-phase region. So we're zeroing in again on our 35 weight percent nickel, which we started seeing was in the two-phase region in our previous slide. We're going to take a look at this composition and cool it down and see how the phase relationships change as we go from it being all in the melt to being in the solid. So we start out all liquid. We have 35 weight percent nickel, and we've got a temperature of 1320 degrees C, and that's labeled as point A on this diagram. They're kind of in the upper center of the diagram at TA, 1320. all liquid. It's up in the all liquid phase portion of the diagram. So there's the composition. The overall composition in phase diagrams is usually referred to as C naught or C sub 0, and that's the composition of the whole alloy, which will typically be different than the composition of any given phase. But because there's only one phase, everything's liquid, that's also the composition of the liquid. So we're going to cool it down. We're going to cool it all the way down to 1190 degrees C. Well, we went from one single phase region straight through a two-phase region into another single phase region. So we're at a cooler temperature, and rather than having liquid, we now have all solid, and it is, since it's all one phase again, and we made that change at equilibrium, that has an average composition also of 35 weight percent nickel. But rather than being a liquid, it's C sub alpha, meaning that's the composition of the alpha phase. And that's the only phase we have. But what if we're right in the middle? What if we stopped our cooling at 1250 C like we saw on the previous slide? Well, now we're in that two-phase region. Although the overall composition is 35% weight percent nickel, the alpha solid and the liquid that are coexisting in equilibrium, there's two phases, they're not the same composition, and neither one of them is 35 weight percent nickel. So if we want to see what the composition of the alpha and the composition of the liquid that are present, we use what we call a tie line. So we draw a horizontal line across that two-phase portion of the phase diagram, and we look at the portion that is touching each of the phase regions. So we looked over on the left-hand side of our heavy black isothermal tie line, and we noticed it touched the liquidus, the boundary between the two-phase region and the liquid region, and the composition corresponding to that touch point is 32 weight percent nickel. So that's the composition of the liquid present for a 35 average overall weight percent nickel alloy at 1250 degrees C. So I bet you can guess what the composition of the alpha solid that's in equilibrium with that liquid is. We'll do the animation. As I'm sure you guessed, it's given by where that same tie line touches the solidus, or the boundary between the two-phase region and the alpha solid, which happens to be at 43 weight percent nickel. So these add up. It's no surprise that these are on either side of the original composition. In order for the overall composition to be 35 weight percent nickel, if the liquid is a little bit deficient in nickel and more rich in copper, the solid's going to have to go the other way. And they will be actually related by the weight fractions of the two phases, which is what we're going to get to next. So we now know that at 1250 degrees C and 35 overall alloy weight percent nickel, we will have alpha solid solution of copper and nickel in equilibrium with a liquid, and we know that the composition of that alpha is 43 weight percent nickel and the liquid's 32 weight percent nickel. But how much liquid is there relative to the amount of solid? Do I have more liquid present or do I have more solid present? That could be important for processing, whether maybe I'm solidifying quickly enough, or can I move my mold? Well, the tie line can tell us that too. So just a quick review here, remembering that we cooled down from TA, where we had all liquid, and if we had gone all the way to TD, we'd have all solid. We can use the ratio of the tie line regions to tell us how much liquid and how much solid we have. So the amount of the weight fraction of liquid, and in this case it's a fraction based on just two phases, liquid and solid, the weight fraction of liquid is the portion of the tie line labeled S over the entire length of the tie line. Likewise, the amount of, or the relative fraction, weight fraction of alpha phase, not composition of alpha, but the amount of phase alpha with respect to the liquid, is the length of the R portion of the tie line, that horizontal tie line over on the diagram, divided by the total length of the tie line. And this should make sense, because if your overall composition is closer to the liquidus, you have probably more liquid present, so the fraction would be given by the opposite side of the tie line. So it's a little bit opposite intuitively depending on how you look at it, but when you are looking for the relative amounts of two different phases that are present, you ratio the portion of the tie line going to the opposite phase boundary over the total length of tie line as a general rule. And then you pick the composition of each of those phases based on the composition of where your tie line intersects each phase boundary. So there's two distinct ideas to get when we're talking about a two-phase region on a binary phase diagram: the composition of each of the two phases present and the relative amounts. So you use that fraction of the tie line to get the relative amounts, and then you use the intersection of the tie line with the phase boundary areas to get what each of those phases is composed of. Okay, and that division of the tie line to get the fractions of each phase present is called the lever rule. And again, that just simply refers to the fact that we are looking to the length from the overall composition to the opposite phase boundary intersection to get the relative amount of each one. And you can think of it as being a bit of a teeter-totter. So you can just take a look at that. And by the way, the tie lines, needless to say, because they are drawn at a single temperature, they are isothermal. So if you're used to thinking in terms of contour lines on a diagram, these are isotherms. So single temperature lines, and they're always horizontal on these binary phase diagrams. So just a little picture of the lever rule to get our relative amounts of phases. You can see that the R and the S that we've divided our tie line into are denoting the relative fractions of alpha and liquid, and they have to balance composition versus relative amounts. So there's another way too. It's kind of a derivation of the lever rule there. The easy way to remember it is just simply to take the length of the tie line, and the relative fraction will be the length of the portion between the average composition and the opposite phase boundary. Okay, we'll do another example here, but we will also look at what's happening microstructurally. So far we've only concerned ourselves with what the composition, well, starting with how many phases are present, where the boundaries between single and multi-phase regions are. So do we have one phase or two or more? Then we've looked at what are the compositions of the phases present, and then we've looked at the relative amounts of the phases if we have more than one. So now we can look and see, okay, what's going on inside the microstructure? We're familiar with the idea that we have grains, and if we have another phase, it'll probably want to precipitate on a grain boundary, and it'll form its own grain, and it'll probably have its own crystal structure. Some will be FCC and BCC, and we can get different things dissolved in each one of them in the interstitial positions or as solid solution substitutions. For instance, our copper nickel is definitely a substitutional solid solution. It's not interstitial. So we're going to use little circles as sort of schematics of what's going on in the microstructure, and these evolved over the years of optical microscopy, where we could actually image what was going on in the microstructure after the fact by rapidly quenching samples and then doing optical microscopy and taking pictures. So we're going to show a series of circles that would be basically representational microstructures as if you had done optical microscopy on the microstructure. So we're going to stick with our 35 weight % nickel, copper nickel binary alloy. Right now it's in the melt, so you can see a big green circle that is looking at a magnified picture of just liquid metal. It's all one liquid solid solution. So when we cool that down to B, we hit the liquidus, and we start precipitating out alpha solid in the liquid, and so we can now see those little particles of alpha floating around as little blue dots in the liquid. The liquid still has an average concentration of 35 weight% nickel, and based on its position over on the solidus, where that horizontal blue tie line hits the liquid plus alpha boundary line on the alpha side, that corresponds to 46 weight% nickel. So those little tiny initial precipitates that we formed when we first started to solidify that alloy were far richer in nickel than the original overall liquid composition. So that is following that solubility phase relationship. So we cool a little bit more, and those precipitates grow. So our alpha solid is still floating around in the liquid, and it's growing. And you can see that the difference in the composition of the liquid versus the average composition of the solid, it's now growing apart. So the liquid is effectively becoming more enriched in copper. Now it's only 32 weight% nickel. It started at 35, so it's lost some nickel. Well, that nickel's been picked up by the precipitates, which are getting, on the average, they have a little bit less nickel overall, but less than those initial precipitates, but still quite a bit more than the average. So at D, we are getting close to being done solidifying. We definitely have more solid than we have liquid. Now the composition of that solid has pulled closer to the average overall composition of the alloy, and that shouldn't be surprising because now the solid is practically the majority phase. It should be close to the overall composition, and the liquid has been severely depleted of nickel. It's much more heavily enriched in copper now. Effectively, you can think that all the nickel has been sucked out of the liquid and deposited into the solid, leaving a very copper-rich liquid behind. Well, eventually we solidify completely, and since we're at equilibrium, the composition averages out. We get really fast diffusion, and so we always stay at a uniform composition, even in the solid. And so now we have all solid. The precipitates have grown together. We've formed grain boundaries between them. So we have a polycrystalline solid there that has one phase. It's all alpha, and it's the same composition as the liquid we started with. So that is a solidification sequence of a single phase, completely solid solution. Okay. We mentioned that this is the case, or phase diagrams only apply if we cool slowly and we keep everything at equilibrium. We're going to take a look at what happens if we cool too fast. And in this case, too fast literally refers to whether or not diffusion in the solid can keep up with the rate of deposition of new material from the liquid, and what will happen if it doesn't. So in this case, cooling at equilibrium has a very specific definition in reference to a mass transport property that we've already studied, namely solid state diffusion. So this is kind of back to that Fickian diffusion concept. So in this case, what we're doing is diffusing copper and nickel back and forth across our growing grain, because the new material that's depositing, we saw here from our phase diagram, is not the same. Every new layer of solid that we add to those precipitates has a little bit different concentration. It's a little bit richer in copper and poor in nickel. Well, for that final solid, for all the way across that grain to have 35 weight% nickel, we have to get all that nickel rich, the nickel atoms in the nickel rich original core, out to the outside to mix with the copper-rich material that's coming down last, that copper-rich liquid. So again, that has to happen by diffusion. So if that diffusion doesn't keep up, we end up with a non-uniform composition across the grain. And this little animation will show you a schematic of what happens in that case. So we're starting with our equilibrium cooling. So if we have a slow rate of cooling, we end up with a uniform composition across our grain, and it's shown as just a big blue grain blob because it has the same concentration. So the color is representing the weight percent nickel in this case. If we cool fast, we're going to end up with nickel-rich core and a copper-rich boundary. So again, the first solid to solidify is 46 weight percent nickel, and then each new layer has less and less nickel, which is being represented by a lighter and lighter color. So in this case, darker color means more liquid. So it's only the last alpha to solidify that has less than the average composition, and it would have to be less because the average has to be 35. So if the core has more, the outer edges of those grains near the grain boundaries have a lot less. Before we go on to eutectics and lamellar structure, an important consequence of having that difference in composition across grains in one case is that we can have a variation in melting point. If we back up to our binary phase diagram and look at it all the way across, backing up here, you can see that our copper, ignoring the animations for the moment here, copper has a much lower melting point than nickel. If we cool quickly and we have a nickel-rich grain center and a copper-rich grain boundary, even if you have an average 35 weight percent overall material, which you would predict to start melting, somewhere just shy of 1200 degrees, if you had a copper-rich grain boundary, it might start melting just a little above 1100. And so if you were planning a thermomechanical process close to what you thought was the melting point, you might be actually performing it above the melting point, and you could suddenly have something splattering with liquid metal in a forging process where you hadn't expected it, and that could be a severe plant safety problem. That used to happen in the early days of steel making and was referred to as a hot short, and was very dangerous in a foundry setting or a hot working setting. So understanding that with respect to processing is very important. Or for in-service properties, if one were to use a cored microstructure in high temperature service, we certainly wouldn't get the properties we would expect from the average. So there's an example of when diffusion does not keep up. Okay, diffusion is really important, and lucky for us, it happens really fast in a liquid. And the fast diffusion that you can get in a liquid can allow us to wildly segregate to nearly 100% ahead of a solidification front and form these fabulous layered structures that occur spontaneously on solidification or on crossing a phase boundary, even in solid solution. These are called eutectics when they form spontaneously upon solidification of a liquid, and they're called eutectoids when they form from another solid, so a solid-solid transformation. And this schematic gives you an idea of how and why they form. Again, this is a spontaneous change driven by an overall energy reduction in the system. Usually when we cross a temperature boundary of a very specific composition, we will have a drive to a solubility limitation drive. We'll go from a liquid where two constituents, in this case lead and tin, are both very soluble together in the liquid, but when we try to solidify them, we find that they are not at all soluble in one another. They can't stand each other. energetically speaking, and they want to form almost pure components of one another. There's very little solubility of tin in lead or lead in tin. So the minute they solidify, they want to segregate into almost pure phases, a two-phase region. What this drives is spontaneous formation of this layered structure where, rather than waiting to segregate in the solid, they kind of do it ahead as the solid forms in the liquid, where diffusion is fast and they can segregate ahead of time. So as you can see, the liquid is solidifying, and what's happening is, in the case of the alpha, it's lead, and so tin is being driven to each side and forming a tin-rich beta phase. And then in the case of the beta phase, lead is being driven to the sides and forming a lead-rich alpha phase. So they're literally swapping places in the liquid very quickly, and when they get to their concentrated, concentrations all lead or all tin, they form a crystal with very little of the other in it, and then that layered structure of almost pure lead and tin alternating layers moves forward. So this happens very quickly, and it forms these spontaneous tight layered structures, and that interlayer spacing is dependent mainly on cooling rate. These can give you fabulous mechanical properties because dislocations will pile up at the boundaries between these phases very, very quickly. They're very hard, and they're basically a spontaneous form of grain refining that you didn't have to do a bunch of thermomechanical processing to get. So we're going to examine how this forms on a phase diagram and get an idea of how and where we would get this based on what we can see in terms of solubility on our phase diagrams, using the same rules we did with isomorphous. So again, this type of spontaneous decomposition of a liquid into two different solid phases at a single temperature and composition is called the eutectic transformation. This is one of the multiple spontaneous thermodynamic phase transformations that we get in materials. These happen in all materials, but they're most noteworthy and plentiful in metal systems. Because we have two components, this is called a binary eutectic. And we're going to use copper-silver for this. It's a famous one, and nice and non-toxic, unlike lead-tin. So on our diagram we have 100% copper on the left and 100% silver on the right. So we're going to use some animated examples to walk our way around the phase diagram. So we have three single phase regions in this diagram. We have the green region, kind of at the upper part, the high temperature region, which is, not surprisingly, liquid. We have a solid solution, so it can have both copper and nickel in it up to a certain point, but it's a single solid phase that's nonetheless pretty much copper rich. Over on the left hand side of the diagram, called alpha, remember I said these go by Greek letters generally, and then we have a silver rich solid solution over on the right hand side called beta, and that's in red. So three single phase regions. And the single-phase solid solutions, they are not very big regions. You can't put very much silver into alpha before it wants to form another phase, whether it's a liquid phase, if we're at temperatures above 779, or forming the beta solid phase, if we're below that. So very limited solubility, and more limited over on the silver side. Beta can take less copper than alpha can take silver. We have a very special temperature in this diagram, and that's TE, which means T eutectic. And that is the lowest temperature at which we will see any liquid, regardless of the composition of the alloy that we are looking at. And in fact, we will only see liquid at that temperature if we're at a very specific composition, and that is the eutectic composition. And so for a eutectic system, or a eutectoid system in fact, you have a single combination of temperature and composition at which we will actually have three phases present. And that is a unique combination of equilibrium, phase, and composition state variables. So it's unique on that diagram. So there's only one point on the diagram where we can have liquid alpha and beta all present simultaneously, and that's the eutectic composition and temperature. So at that composition and temperature, all the liquid present, which will be all that's present at that point, if we cool along that composition line, will spontaneously form alpha and beta at the same time very, very quickly with that layered solidification front that we saw in the previous slide. So that's known as the eutectic reaction. This is not a chemical reaction. We're not swapping electrons the way we would if we were breaking and forming chemical bonds, but we are having a dramatic rearrangement of composition and phase. So it's akin to a chemical reaction, but not quite. But it definitely has a thermodynamic drive the way a chemical reaction would. So this occurs in this system at the eutectic composition, which is 71.9 weight percent silver. And at that composition and at 779 degrees C, all the liquid present, which is all the material present, because if we're cooling, it started out as all liquid at that composition, will spontaneously form alpha and beta completely. And the alpha that's formed will be 8 weight percent silver, and the beta that forms will be 91.2 weight percent silver, which are the compositions at the endpoints of that eutectic tie line. And they're present on the diagram. They're in black letters. So we'll go back to our unfortunately more toxic binary eutectic system, lead-tin, which was historically interesting as a solder, and that is because of its eutectic transformation. It all solidifies at a single temperature and makes it a little bit easier to do hand soldering. So in this case, our eutectic composition is 61.9 and our eutectic temperature is 183 degrees C, much cooler system. So we're going to look at a different composition in this case, kind of look at maybe at heating it. If we started out at 40 weight percent tin, so 60 lead, 40 tin, as our average composition, and we heated it up to 150 degrees, we wouldn't melt it. We'd still just have alpha and beta present. And what would their compositions be? Well, alpha would be 11% tin, and beta would be 99% tin. So beta has a very low solubility for lead. It's almost pure tin. So it didn't take much, only 1%. And I guess the last question we could ask ourselves about this particular alloy at that temperature is, what are the relative amounts of alpha and beta now that we know what their compositions are? So we apply the lever rule again, and so we say the amount of alpha is not R over R plus S, but S over R plus S, which could also be said to be the composition of the beta phase minus the overall alloy composition divided by the composition of the beta phase minus the composition of the alpha phase. So that's 0.67 weight percent alpha. And because we've only got two phases, we automatically know the weight percent of beta, which is 1 minus that. So it should be something like 3.3, or excuse me, 0.33, which would again be R over R plus S for the weight fraction of beta. So if we have a composition and a temperature, we can look at our phase diagram and determine the composition of both phases and the amount. So far this is not any different than we did with isomorphous, because we haven't approached the eutectic transformation coming down from above. We've only looked at a two-phase region like any other two-phase region. So in this case, now we're going to look at what would happen at higher temperatures. What if we took that same alloy and heated it up? So now we are in a two-phase region, alpha plus liquid. So we look at where our black dot is and go up. Okay, there's no more beta. It's gone. So we consumed all the beta and turned it into other things, mostly liquid in this case. So now we should be in a situation that's much more akin to what we saw with our copper-nickel phase diagram, where we just had liquid and alpha. In fact, we have the same Greek letters. So just like that case, we could ask ourselves, well, what's the composition of each one and how much are there? So we apply exactly the same rules. In this case, our alpha is 17% tin, and our beta, our liquid, no beta, our liquid is 46% tin. And we should have a bit more liquid than alpha. So we have 21 weight percent alpha and 79 weight percent liquid. Okay, we will look at now the far left-hand side of our eutectic diagram. We're still in the lead tin system, but now we're looking at the very, very lead-rich side. So we are now over here on the left-hand side of this diagram and all blown up. So now we're kind of only seeing just the very left-hand end of the eutectic tileline, and have zoomed in on this alpha region, which is mostly lead with a little tiny bit of tin. So what if we took an alloy that only had 2 weight percent tin? And so that's represented by the purple line, which is C0 of 2 weight percent tin. So we can see that if we cooled that, we would go from the liquid, we would drop through a liquid plus alpha two-phase region. Eventually we would solidify all of it to alpha, and right before we got down to room temperature, we might start grazing the edge of that alpha plus beta two-phase region. So if we looked at microstructures for that, we would say, okay, we start out in a liquid, all one phase, it's all liquid. And again, we went through that two-phase liquid plus alpha region, slowly consuming the liquid and depositing more of it as our alpha solid. Once we dropped below the solidus, the alpha side of the liquid plus alpha two-phase region, we now have all alpha. And since we didn't enter the alpha plus beta region, that's what we had all the way down to room temperature. And down to room temperature is important in this case because that's where things stop diffusing, and in some cases, even if you crossed a phase boundary, around room temperature, metals don't diffuse fast enough that things would change. So even if you crossed a boundary into another equilibrium regime, you might not actually see that phase transformation just because it's too slow. And that's very important for a very important strengthening mechanism that we'll look at called precipitation hardening, where we do that on purpose, and then we go back and give a little bit of heat to our material and allow that equilibrium second phase to almost precipitate, and effectively load the microstructure up with more strain fields and make it very strong without losing much in the way of fracture toughness. So it all starts with this particular shape of a phase diagram. So the alloy that we're considering now, C0, that's between 2 weight percent tin and 18.3 weight percent tin, is an example of the type of alloy composition that would be amenable to this type of hardening. And we'll start to look at why right here. So if we cool all the way to room temperature, we would theoretically get an alpha plus beta microstructure two-phase region. So in this case, we're going to end up with alpha grains with beta phase particles that precipitate at the grain boundaries. So we'll kind of step through how that happens. So again, we're starting in the liquid, different composition liquid, but all liquid. We'll cool down through the two-phase region. We'll start to precipitate alpha. We'll get to a point where we have consumed all the liquid, and now we have just nothing but alpha. Now again, this is a different composition alpha than we had with our 2 weight percent tin. It's much more tin rich here. Looks like we got, like I said, a little less than 18.3. Maybe we have 17 weight percent tin, and all the alpha is 17 weight percent tin. Now if we cool down a little bit more, down to maybe say just above what looks like 100 degrees C, just from that last black dot, we've now entered a region where beta is stable, and it starts to precipitate from solid solution. And I'd say this optical micrograph might be a little bit misleading because it's showing that beta as precipitating in the middle of those alpha grains. I will make a verbal correction to our animated slides and say that a lot of those red beta particles, in fact the majority of them, should probably be shown precipitating on the grain boundaries. That's the high energy part of the microstructure, and it's where diffusion is the fastest. And from the time that we hit the alpha solidus, we were dealing all with solid phase movement. So to make these phase changes and to move the tin and the lead around in the microstructure, we are relying on diffusion. So we know darn well that this will probably mostly be precipitating at the grain boundaries. But nonetheless, we do have two phases there. And so that's what the red dots are showing, that we have beta phase. I'm just making a debate about exactly where it's likely to be present in the greatest abundance. Okay. We have a special circumstance if we have the eutectic composition and if we are cooling from the liquid. This is where we get that beautiful lamellar structure that has all those great mechanical properties. So we're going to walk through a eutectic solidification. So say we have the eutectic composition, 61.9, and we start with a liquid of eutectic composition. So it is 61.9 weight percent tin, the rest being lead. We start with a liquid, we're going to cool it. The minute we drop below, or actually the microsecond we drop below 183 degrees C, we instantly form that lamellar structure. And instant doesn't necessarily mean instantaneously. It probably takes a few seconds, microseconds. But it is near instantaneous compared to the rate of solid state diffusion, which is what it would be competing with in most other microstructural transformations. This is one of the fastest microstructural transformations known, and mainly because all of the atomic movement, all of that segregation is going on in the liquid phase, where diffusion is several orders of magnitude faster than a solid for the same temperature. So we went from homogeneous single-phase liquid in the green to the lamellar structure, which is going to grow and impinge on other lamellar fronts that are coming in from different directions, and will actually end up with a randomly oriented zebra-striped structure of alpha and beta in very, very thin slices. That's what lamella means, little plates, little stack. And within that eutectic microstructure, the lamella, the alpha slices, the little blue slices, they're all alpha. They have a composition defined by the end of the tie line at the eutectic tie line at 18.3 weight percent tin. And then the beta, the red slices, the red lamella, have they're much more tin rich at 97.8, and I bet you can guess their relative fractions by the Lever law. We won't go through that on this slide because you already know that at this point, or can work it out with some problems. And here is a real-life picture. This was repeated from a previous slide, but these are eutectic lamella colonies growing into one another and assuming effective grain boundaries. Okay. Well, what if we have halfway in between? What if we're not right at the eutectic composition, but we're going to hit the eutectic tie line at the eutectic temperature? By the way, you only hit the eutectic tie line at the eutectic temperature because, being a tie line, it is isothermal. So only one temperature, TE. So this will be any alloy in this case which goes from 18.3 weight percent tin, which is the left-hand side of the eutectic tie line where it intersects with the pure alpha region, all the way over to the beta boundary at, I believe, 97.8, and with the eutectic composition being in the middle at 61.9. So we're going to take something that's kind of in the middle there at 40, and we're going to cool it down and see what kind of microstructure we get. So we start in the liquid. When we hit the liquidus, and that's the boundary between the liquid and the liquid plus alpha two-phase region, will start to solidify, and the first phase that will form as a solid is alpha. We will continue to form more of that as we cool down through the liquid plus alpha region, and that's shown schematically over on our little microstructure circle over to the right, where those alpha particles are slightly bigger, those blue alpha particles in the green liquid. And now we are right above the eutectic temperature. So when we cool down below T eutectic, TE, shown in the purple over on the left-hand side, all of the liquid that is in the green is going to go through the eutectic transformation and form that beautiful lamellar structure and consume all the remaining material. And we can calculate what the composition of that liquid is. We actually don't need to calculate it. We know it is the eutectic composition. That makes it easy. But we can calculate the fraction of what we call primary alpha, meaning alpha that formed before the eutectic, versus the amount of liquid that will become eutectic lamella, which will nonetheless contain alpha, but it's alpha that formed in a different way. So here's what it looks like once it drops to the eutectic. You can see we have another microstructure circle on the lower right-hand part of the diagram, and it's all blue and red. We have the same exact primary alpha that was there before. That has not changed at all. What happened was the green liquid went through the eutectic transformation. It turned into eutectic alpha and beta in the lamella structure and formed its own grains. So we now have two sources of alpha. Alpha that formed before we went through the eutectic transformation, which is called primary alpha. And then we have alpha that formed as a result of the eutectic transformation, and that's called eutectic alpha. We only have one source of beta, so we just call it eutectic beta because it formed due to the eutectic transformation. And we can again use the Lever law and use our eutectic tie line in this case to determine compositions overall and of relative fractions of each component. Of each phase. Okay, special vocabulary words, hypo and hypereutectic. If we have a eutectic transformation in a phase diagram, compositions that are to the left-hand side that are less rich in the component that we're indexing across the diagram, those compositions are called hypoeutectic, meaning below, and those that are richer in the indexed composition are called hyper. So in this case, any alloy that has less than 61.9% tin would be a hypoeutectic alloy, and anything more would be a hypereutectic. If you're right on the eutectic composition, you will say this is eutectic lead tin. And so this animated arrows shows those two regions, along with the type of microstructure we would assume to see. So in this case, if you follow the very pale blue arrow, you can see that we're getting primary alpha that forms up in that liquid plus alpha region, and then all lamella eutectic for what happens to the remaining liquid once it goes through eutectic transformation. And a totally analogous situation with the pink arrow, where we formed hypereutectic or primary beta in the liquid plus beta region, and then when we got down to eutectic temperature, all of the remaining liquid formed eutectic again, the lamellar structure. So same kind of situation with a single phase forming first, and then when we drop down to eutectic temperature, all the remaining liquid forming this characteristic lamella. Very important thing to note, since the eutectic forms last from the remaining liquid, it is the continuous microconstituent. Now, we don't call it the continuous phase because as a eutectic it is by definition at least two phases, but we call it a microconstituent. But whatever properties it has, will tend to determine the properties of the overall material. So we could have a lot of that primary alpha or beta, but it's generally going to be the properties of that lamellar-eutectic that dominate, even if you've got some of the primary material present. That's really important to remember about eutectics. They are by definition always going to be continuous when they form, if something doesn't transform in them after the fact. And because of that, their properties will, all other things being equal, tend to carry those of the material. Lucky for us, they tend to have good properties that we like, but not always. Okay, special constituents. These are components. Intermetallic compounds. There are certain metals that like to sit in association with one another. These are almost akin to a ceramic bond. They're still metallic bonds, but a lot of them have quite a bit of covalent flavor to them. They tend to be very, very stable. They melt at extremely high temperatures, and many of them have very limited solubility for other things in them. Ones that have almost no solubility to either side are called stoichiometric compounds. And this Mg2Pb, or magnesium plumbate, I guess, could be one way you'd call it, probably not. But it's a magnesium lead intermetallic. It's practically a stoichiometric compound. Some of these will be wider, so it'll form a little single phase, single component region on a phase diagram. These are very special because we can treat them like components in the middle of a phase diagram. So you can see here that we have, although our main components are magnesium metal and lead metal, the main portion of the phase diagram right in the center, where we would be if we had, say, 50% magnesium at 300 degrees C, we're actually in an alpha plus Mg2Pb region, where the Mg2Pb intermetallic is both a phase and a component, effectively. So those lend a little bit of complication to the phase diagram, but if you think about them as a single phase region and a sort of a pseudo-constituent, component, that makes it a little bit easier. These are very valuable from the standpoint, especially of high temperature properties. So if we take a look at some things like high performance nickel superalloys, you'll see several of these in the diagrams. But those are, there are many metal systems that form these. And a ceramic phase diagram will consist almost exclusively of these. So you will see them. Okay. Going on to a very, very special system, iron-carbon. This is the parent system for all steels and all cast irons. So as that represents at least 50% still of a lot of our structural materials, certainly the majority of our structural metal alloys, it's something that we're going to study in great depth in this course. And it also gives us a nice showcase of several of our characteristic phase transformations. As you can see right there, kind of in the middle, we have what you probably can recognize as eutectic over at 4.3 weight% carbon and 1148 degrees C. And then we have something else that looks an awful lot like it, but is not quite, the austenite to alpha plus cementite, ferrite, and cementite eutectoid transformation, which is very important for steel making. So we'll just kind of walk our way through that. So again, we have our eutectic at point A, and that's over in what we call the cast iron side of the diagram. Point B is our eutectoid at 0.76 weight% carbon, and that's over in what we call the steel side of the diagram. And by the way, those two are differentiated by the left-hand side of the eutectic tie line. So the end of that gamma region is kind of the barrier line between steels and cast irons. So you can see that the eutectoid tie line goes all the way across from 0.76 weight% carbon to 6.7, which is where we have another intermetallic or stoichiometric compound, iron 3, carbon 1, which also goes by the name of cementite. So it's another one of those mineral nomenclatures. And again, we usually treat it as its own component in the phase diagram, as if it's another metal. So if we look at single phase region there for austenite, labeled gamma for the phase, that's a single phase region. Obviously we have a single phase region for liquid, and then we have another very small one at nearly pure iron and at very, very high temperatures. That's another body-centered cubic solid phase labeled delta up in the green. So those are the three: gamma, liquid, and delta, and then alpha, very, very pure iron down at lower temperatures in the aqua. So we got 4 actually single phase regions in the diagram. And just stepping through some microstructures. Just a little look-see there. If we look at eutectoid steel, cooling something down from somewhere in the austenitic regime at our first black dot that we showed, where we have all gamma phase, single solid phase. If we drop down through the eutectoid temperature, much like we did with the eutectic temperature in the lead-tin phase diagram, we suddenly form the eutectoid, which looks very similar to eutectic. We've got another lamellar structure. These tend to be finer because now, rather than having all of that segregation happening in a nice fast diffusion liquid, it actually, all that stuff has to scramble around within the gamma solid phase. So it's a much, much slower transformation. But it still happens, especially given the fact that it's happening still up at 700, almost 730 degrees C, where even in solid state gamma, diffusion is still pretty fast. So we get something that looks very similar to a eutectic, but it's finer. And in this case, we have alternating layers of our alpha ferrite, our aqua alpha phase, and cementite, our practically a ceramic intermetallic iron carbon constituent and pseudophase. And just like we had hypo and hypereutectic, we can have hypo and hypereutectoid compositions, either to the deficient or enriched side of the eutectoid in terms of composition. So we're looking at C0 in the aqua dotted line. That's a hypoeutectoid steel because it has less carbon than the 0.76 eutectic, or excuse me, eutectoid in the gray, ending in the gold dot. So if we looked at that up at around 1000 C, it would be all gamma. And then as we cooled it down, it would hit a two-phase gamma plus alpha region. And this time we are definitely seeing that alpha forming on the gamma grain boundaries. In steels, one of the most important things we can do is control the size of the grains in that austenite, that gamma region, because everything that forms after will be controlled by those. It starts on them, and its eventual size will be determined by the size of those prior austenite grains. So when you think about grain refining in steels, it starts up at the high temperature phase, even if that phase isn't there. When you use the material, it's set the scale. So we grow that alpha, and it connects eventually. It becomes continuous, starts growing along the prior austenite grain boundaries, and then whatever austenite is left forms eutectoid. The eutectoid microconstituent, those layers of alpha ferrite and cementite in steel, is so important from a properties standpoint. It's so important historically. It has a name, even though it's not a phase. It's a two-phase microconstituent, but it has its own name. It's called pearlite. And history of steel making there. So we call the eutectoid microconstituent in steel pearlite. That's a lot easier to say anyway. And this is what that type of microstructure would look like for real in an optical micrograph, where the large white grains are the proeutectoid ferrite that have grown on the prior austenite grain boundaries and formed their own grains, and then the lamellar pearlite or eutectoid phases microconstituent having corresponding to all of the remaining austenite that was there. So this is a reasonably low carbon steel, just judging from the ratio of alpha ferrite and pearlite present. And again, like we can in any phase diagram, at any point we can look to our tie lines for the compositions of the phases present and the relative amounts. So right before we dropped down through the eutectoid transformation, we had about even-steven amounts of ferrite and austenite. And then, of course, once we dropped through the eutectoid, we had quite a bit more alpha ferrite than cementite, because now we're referencing all the way back on S, that red S line to cementite. So we're way over to one side of that lower tie line. And we can apply the lever rule there too. So we can do the same thing on the other side of the eutectoid composition. So this is shown in our red composition. So we've got somewhere above 1% carbon now. This is called a high carbon steel, or a hypereutectoid steel, and it's going to have very, very different properties, and we're going to see why in just a second. Just like we did with the hypoeutectoid steel, when we're up in the austenite regime, hey, it's all austenite. The only difference is there's a lot more carbon in this austenite. So we're going to start dropping the temperature. We are going to hit the gamma to cementite two-phase boundary, and we're going to start precipitating and forming hypereutectoid cementite. So we have little red phases forming. So instead of nice soft alpha ferrite, this is pretty much a ceramic that's forming on the grain boundaries. This is some pretty hard stuff. And as we got down towards the eutectoid composition, we started depositing more and more of it. As more and more carbon left the austenite, it formed more and more cementite on those grain boundaries. That red cementite is now coating completely the austenite grains. We now have a very brittle material as the continuous phase. This is one of the reasons why high carbon steels have to be used with caution. This material would be something to be cautious of from a fracture toughness standpoint because of the presence of that continuous cementite phase. And whether or not it had enough fracture toughness for a given application would be mainly dependent on how thick that layer was, and whether or not a crack traveling through it would be in plane stress or plane strain. So see, all these concepts suddenly come to bear. So when we drop through the eutectoid temperature, all of the remaining austenite transforms into pearlite, and we get the microstructure that's shown schematically over on the left with the red and the aqua, and for real in a photomicrograph down in the center. And given the way the etch works, cementite and ferrite both etch white. So the white coating the grain boundaries is the pro-eutectoid cementite, which was shown in the red in the schematics, and the remaining material obviously is pearlite. And so you can see from here we don't have a lot of primary cementite relative to the amount of austenite prior to eutectoid transformation. So we've got a relatively thin layer of that continuous brittle cementite, which is good. Otherwise this would not be a fracture tough alloy. So much more pearlite than cementite in this case. And we can, again, go through the lever law, and we can look to the boundaries of our tie line for exact compositions. And you will be highly encouraged to go through a few of these and actually do the calculations and walk your way quantitatively through the phase diagram. Depending on where you're taking this course, that might be one of your homework assignments. And in fact, here's one example that we could walk through for a hypoeutectoid steel at 0.4 weight% carbon. We'll just take a quick walk through the phase diagram for that one. So there's our C0. We can see it's hypoeutectoid. It's on the left-hand side of the eutectoid. And we'll just walk it down through, looking at the relative phases and compositions just below eutectoid. So we had a weight fraction of cementite of just under 6%, And so that means in any 100-gram sample we had 6 grams of cementite, which is far less important than the fact that it was not continuous. So all the cementite in this, of course, remember, is coming from the perlite. There is no pro-eutectoid cementite in this one. And again, just looking at other parts of that same sequence, we can look at how much austenite and perlite are present right below the eutectoid transformation. Excuse me, alpha ferrite and perlite. Apologies. Other side of the Liebert rule. Okay, so far we've just talked about carbon and iron in the iron carbide phase diagram, and that's appropriate because if for this course we're only covering binary phase diagrams, and so that's our two constituents. It's binary. Steel in modern metallurgy is almost always more than just iron and carbon. Even what we call plain carbon steels tend to have a few other alloying additions just to manage impurities and allow for processability. We do put other alloying additions in specifically to drive hardenability, toughness, corrosion resistance, etc., without ever encroaching on the realm of, say, stainless steels or ferrochromes or high nickel. These are what we call low alloy steels, where we'll put any one of these elements shown here on this diagram in specifically to alter properties, usually mechanical properties. And these will be present in somewhere less than 5 weight%, quite often less than 1. One of the side effects that these have is that they will change the eutectoid temperature. In some cases, they'll shift it significantly. And again, what we're doing is going to a ternary system, so we're effectively changing chemical potential or composition simply by adding another alloying element, another constituent. So this diagram just shows you a quick glimpse of how the eutectoid temperature would change if we added up to 12% of all of these different things. And one trend to look for is how much that eutectoid temperature changes as we add very small amounts of anything, and what indication that has on things like solubility. So titanium, doesn't take much titanium to shift that eutectoid temperature way up. So if you were processing your steel, something with a 2 weight% titanium, the eutectoid temperature could well be up close to the melting point of the alloy, and so you effectively would have a very different sequence of microstructures on cooling. The whole phase diagram would look different. The others, definitely less drastic changes, but still big shifts. So a lot of the things that were happening at 700 degrees C would be happening at 800, or would be depressed in the case of nickel and manganese. So it would happen at a cooler temperature. And in addition to shifting up and down, when we add alloying elements, we will shift the eutectoid back and forth. In fact, anytime we add another component, any phase boundary, the temperature composition corresponding to any phase transformation reaction, eutectoid, eutectic, paratectoid, monotectic, there's several of these, all of these will change position because we are effectively changing another state variable. But in the case of steels, the changes are small enough that we don't think of it as a whole different phase diagram. We can just think of it as the same one shifting around. And if you go into alloying development, or you're selecting an alloying particular steel alloy, or you're working with a heat treater or a metal supplier, you'll keep these kind of changes in mind when you think in terms of things like cost of processing and eventual properties, because the placement of these reactions on the phase diagram have big implications in processing ease and cost to whoever you're working with, which will of course be passed on to you. Okay, that is it. A very long lecture for the day. Apologies, this has been almost an hour and a half, but we have walked through all the essentials of phase diagrams with respect to the concepts of solubility, state variables, the ones we use, namely temperature and composition, the fact that there are others that you might use as you go into different fields or processing regimes, and the very basics of isomorphous and eutectic and eutectoid. I will tell you that there are several other phase transformations that you might concern yourself with if you end up especially in metallurgy. We won't go over them in this course, but they're out there. If you're interested, you can see your instructor for the class to learn even more. And we will definitely be revisiting eutectic, eutectoid transformations specifically in light of metals processing for steels through the martensitic transformation, and especially aluminums and beryllium coppers with precipitation hardening. So everything you saw today will set the stage for you to make some amazing materials spontaneously with thermodynamics and processing in microstructural transformations, which will be our next topic. See you then.